So, good morning, everyone. We are now starting with the webinar. So this is Nandeep from MIDAS, and this session is in continuation with the earlier series. On public demand, this session has been added with design of Eurocode for the box cutter balanced cantilever bridge analysis. Okay. Now, since this is a mass webinar, the attendee mic have been muted. If you can hear my voice, please raise your hand by clicking on the button shown by number 2. Okay, so I have enough raised hand. Be continuing with the webinar. If you have any questions during the webinar, please type those in the box shown by number 3. And a document with answer to all the questions would be sent within a week after this webinar. Okay. So in the earlier sessions, these are the topics that were covered: the material properties, the section properties. The model was created using the FCM wizard. The tendon properties were defined, the tendon pre-stress. The substructure was later manually modeled. The groups were defined, the support conditions were defined, the different loads, that is self-weight, SIDL, moving loads were applied. The time-dependent material properties were defined, which was used for the construction stage. After the analysis, the detailed analysis report was shown, and the results with different loads combination were also shown. Now in today's session, this is what we would be doing. We would be adding reinforcement to the sections. We'll be checking the camber for the balanced cantilever bridge. What is the camber correction that is needed at various stages? We would be performing the response spectrum analysis for X, Y, and Z directions. We would be viewing the tendon losses. We would be designing a certain sections as per the Eurocode. And I'll also show the dynamic report that is generated. So let's get started with the session. So first of all, what I would be doing is I will just be creating the superstructure very quickly, because today I also wanted to show how to give the tendon profile from the wizard itself. So I would be giving a couple of tendons from the wizard itself. So the sections as well as the material property needed have already been defined. So I'll just go to structure, FCM bridge. Let's select the materials. The pier section, the stage duration. These are all the things that were covered already in the previous session. So quickly just going through these. The height of the pier we are keeping as 20 meters. The fully supported method on the fully supported span on the left edge. Similarly on the right side. the Barron's cantilever part. If you are doing it by type 1, you could enter the section dimensions for the section at the support and at the center. But since you have already defined the sections, we'll be using that one. So at the center, we'll be taking the ground support. Okay. The peer table will be taking the okay, yeah, that section is not defined, so I'll quickly import that section. Near peer section. Okay, it's there. So at the center we are taking ground support, the peer table we are taking the near peer section, the diaphragm we are giving as the internal diaphragm. So the section would be tapered from this to this. Now to enter the tendons. Okay, so we can give the number of tendons that need to be entered. For that you can click on this tendon number. Okay, so these are the various group names and the locations where tendons would be given. Okay, so say PSTG group. Say there are 4 tendons in the PSTG group. Similarly, there are some number of tendons in PWTG. So accordingly, you just have to select the number of tendons and at least the location for these tendons should be created. Now, since ours is a single cell, there's symmetry besides the center line. So position for us is 1 only. But had it been 2 cell or 3 cell, then there would have been different positions. Because accordingly, you would have to select the number of tendons for each position and then you will have to say OK. So, okay. Okay, so now these are the tendons which have been created. Now we have to enter the locations for the baselines and the other locations as shown in the FCM tendon viewer, the BI, HI values. Okay, but since these are too many, I'll be just entering for say PSTG1. Okay, so I'll be removing the other groups. Okay, so say the baseline, that is the distance of the group or the baseline that you are considering from the center of the cross section. Okay, so say this is 3500 mm for this case. So this is the baseline. As you can see from center, the baseline is shown. Then say BI, that is the distance of the tendon from the baseline. Say I am entering this as 1000 mm. So this means the tendon is 3500 plus 1000, that is 4500 mm from the center of the section. Say HI for tendon, that is at the if you view along the longitudinal direction, at the center what is the height of the or the depth above the top slab where the tendon is. So let's say this is 150 mm. Then anchorage. So how deep is the anchorage setting? So let us say this is 150 mm. Then this is BI for anchorage. So what is the anchorage location from the baseline? If the tendon has any curve or anything, then the anchorage would be towards inside or outside accordingly. So let us say BI for the tendon is let us keep BI as same, it being in the same line, a straight tendon. Let us say the anchorage is 450 or 400 mm below. So HI would be 400. RI is the angle that the tendon would be making. So let us say this is 20 mm. And let us give theta as shown in the figure as 30 degrees. Okay. So now for the other tendons, we just need to edit some data. So we can copy paste the data for the remaining tendons. Let us say we are changing BI to 750. HI is the same. AI will also remain the same anchorage setting. Again, the B for anchor it changes to 750. H again stays 400. R also 20 and theta is 30. So similarly 500, 500, 250 and 250. The select tendon property is 17 to 15, which was already defined. Let us say okay. Okay. Tendon profile data. So, I'm changing the baseline dimension. It seems it's going out of this section. Okay. Wow. It seems it's creating some issues in giving the coordinates. I used this model in the morning and so I'm unable to give the profile over here. So anyway, I guess I'll just move on with the model that was already made in that case. This just creates the superstructure. So this was the model that was previously made using all the tendons and all the profiles. So we'll start by how to give the reinforcements. Okay, so these are already provided. So you have to go to properties, section manager, reinforcements. Okay, so these are the sections. Now to provide the reinforcement in this section, you have to click on this section. Okay, then usually we provide a cover to the reinforcement. So say the cover provided is 50 mm. So it goes, the guideline is shown in this section. It is 50 mm inside the section dimension. We have to give the reinforcement now. So say there are two ways. Let us go for input B. So we just have to click in the section where we want to give the reinforcement. So if we click over here, we extend it to this point. Okay, so this line is drawn. Say we are giving center to center distance as 200 mm. We are giving the edge bar as well, and the bar is P12. Okay, we say add. So this reinforcement is now added. Similarly, we have to add reinforcement for other locations. If you click at a wrong point by mistake, you just have to go back to the starting point and click again. So this way reinforcement has to be provided for all these sections which we need to design. So these are the longitudinal reinforcements. Okay. So now once this is done, we have to click apply. Then we have to give the shear reinforcements. So for the shear reinforcements, these are already mentioned, but say I'm keeping my pitch as 200, the angle as 90 degree, that is angle of the shear reinforcement with respect to the horizontal, and say this AW I am giving as 804.24. Okay, now if I know the area of the reinforcement, then that is good. But say I know the bar and the number, then I can simply calculate it. Say I'm taking P16 bar 4 numbers, so that is 804.24 mm square. Okay. Similarly, the torsion reinforcement we can define, we can give the number, and if we know then well and good. If we don't know, then we can enter the number. Say AWT, in this case I would like to enter as 804.24 and ALTS 20584. Okay, and the enclosing stirrup, that is a stirrup in which encloses or which is in the shape of the box, which is, if it is covering the flange as well or it is there in the flange as well, then you have to click on include flange cantilever. Otherwise, with a cover thickness of 50 mm, the enclosed stirrup is made. Once this is done, click on apply. So the reinforcement for the selected section have been provided. Now if you want to design more sections, then you have to provide reinforcements for all these sections accordingly. Okay. So once this is done, now I'll be applying the response spectrum function to this model. So we'll go to load. We'll go to Seismic, the response spectrum function. We say add. Okay. So here you can give the design spectrum based on different codes. You may select Euro code, you may select the options over here, and the design spectrum will be generated by itself. If not, if you have your own design spectrum and you want to make it according to that, then you could copy paste the data from Excel sheet as well. So say this is the Excel sheet with the data. So I'll just copy and I'll paste it here. So this user defined response spectrum is generated. Say okay. So once the response spectrum is generated, we'll have to give the response spectrum load cases for that. So say response spectrum for UDF. In X direction, if I want to give, then I have to select direction as XY, keep excitation angle as 0, the scale factor is 1, use the user defined function and say description in global X and add. Okay, now if I want to give in Y direction, then I have to change the excitation angle to 90 degree. Change description to global Y and add. Sorry, RS Y. Add. I'll modify this name as well. RSX. Okay, and for the Z direction, give name as RSZ, the direction as Z, the scale factor as 0.67. It's 2/3 in vertical direction, it's 2/3 that of the horizontal direction. So add. Now if you want to modify some data for the eigenvalue analysis, then you can go to eigenvalue analysis. You could either select Ritz vector, change the number of frequencies. So over here we are saying number of frequencies as 20 to generate 20 mode shapes. Say okay. Okay, close. So now the response spectrum function and the response spectrum case have been added to the model. Okay. Now say we want to add the settlement analysis to this. So for doing that, again we go to loads, we go to settlement, okay, and we select the settlement group. Now settlement analysis is done for the superstructure. So instead of settlement for the pile and its element, the settlement groups have been will be created for the pier bottom. Okay, so we'll create and say we are going for a case where the two piers on the left and the one pier on the right are settling by 10 mm. So we are going for settlement of 3 piers. So I'll be creating groups accordingly. Say P1 settlement of minus 10 mm. Node list. I'll select this select by window option. I'll select the node. I'll say add. Similarly, the second one, group name is P2. Click on node list. Select the second node. The settlement is already minus 10 mm. Say add. And similarly for the third group, first I'll write the name P4 node list and add. Okay, so these 3 nodes have been added for settlement. Similarly, we have to, just the way we created response spectrum load case, similarly we have to create the pier settlement load case. So select the 3 piers and we just have to give the name settlement say and we click on add. Okay, so the settlement load case has been created. Now for creating the load combinations, we'll go to results, to load combination. Okay, we'll go for auto generation. So we'll select Eurocode 0 over here. The load combination for static plus construction stage, we'll consider both the factors, where one is leading, where is accompanying, and say okay. So automatically the load cases are generated. Okay. Now for PSC, we'll select the code as Eurocode. We go to parameters. We'll select all the parameters. Use the recommended NX. Besides that, there is British and Italy NX. Pre-stressing steel as smooth bar and wire, and say okay. Design material. Now, though we have selected the material, means we have defined the material at the start, for design we need to assign the reinforcement as well. So the material is selected. After that, the code is selected for the reinforcement and the class is selected. So you'll see that Fy and Fis of 600 Newton per mm square is added. This needs to be done for all the material for which design needs to be performed. Click on modify and close. After that, we need to select the design and output position. So these are the locations for which the PSC design would be performed. If we select all the members, then the preparation of design and the design report itself takes a lot of time. So we'll be performing design for selected members. So we go to design position, and we can either select the element in the model view like this, and add and replace moment resistance at INJ, apply, or we can click on these three dots over here if you know the element number. Okay, so say I wanted to add for 17 and 28 only. I can simply enter, say 27 I have deleted, so I can simply enter 27 over here. So INJ is already added for that. So this is how you can add the elements. So these are the locations for the PSC design. Similarly, locations for PSC output have also to be selected. Click on three dots again, and as you can see 17 and 18 are already there for moment, positive, negative, as well as shear and torsion. Now serviceability load combination types. So once the load combinations are created using the auto generate, the quasi-permanent, frequent and characteristic load combinations are automatically taken for the PSC design. So say for quasi-permanent I am saying, so it is combination 81 to combination 89. Okay. Now if I go to results and load combinations, the ones that we created before, if you'll notice the 81 to 89, these are the quasi-permanent cases, so they are automatically added to the serviceability load group for the PSC design. Okay. Similarly, long and short term losses, sulfate and SIDL are kept in long term, rest are kept in short term. The exposure class, say we are selecting XC1 in this case. Okay, so XC1, we have to select the model in the, we have to select the element from the model view. 17 and say this 26 now. So we go to unselect by window and select and say this one 17 and 28. Say XC1, apply. Okay, so XC1 load class has been exposure class has been selected for these members for which the design would be done. Okay, but before we perform the design or do anything else, we have to perform the analysis. Performing analysis on this model will take some time, about 5 minutes or so. So again, I have made a model with the finished analysis. So this is the model with the analysis performed. Now to check the camber, first the analysis needs to be performed. Then a certain set of structure groups are to be created. Okay. So the groups that are created for the camber correction or rather camber checking are the main girder element, that is the box girder elements, wherein all the box girder group wherein all the girders are there. Okay. After that, the support nodes, that is the place where the deck is supported at the mid. So these are the support nodes. Okay. And besides that, a group with all the key segments. So these three groups need to be made if you want to check camber, because once you go into camber reaction, FCM camber and FCM camber control, the camber control asks you to select these groups, the bridge girder element groups, the support node groups, and the key segment group. Okay, so that is why these groups were made. After that, to check the camber in the graphical format, go to camber reaction, FCM camber and FCM camber graph view. Say for the summation load case, which includes the dead load, tendon, primary, secondary, everything, we say OK. So this camber control graph is made, wherein this location where it's almost horizontal and least, that place is the key segment near the left span. This over on the right side is the key segment near the right span, and at the center where it is very high, again a straight line, that is the location near the rather mid key segment. And from node 15 to node 18, where there's one sudden vertical jump and then it increases or decreases uniformly, this is the peer table. Peer table to the left. Similarly, node 38 to node 42 is the peer table to the right. So this is the graphical view. If you want to check it in the table format, we go to FCM camber table. Again, we select the same load case and OK. Okay, so it's coming in 4 pages. So let us go to page 2. So for node say 15, 16, 17, these are the various cambers. I'll go into mm for better result. Okay, so as you can see, at the initial stage the camber correction required is high, and in the final stage, that is the 14th stage, it reduces to 0 for all the nodes. That is, at the end it's a totally horizontal span. So during several construction stage, and that is where this camber control becomes really important for the balanced cantilever bridges. Okay, we'll again go to the model. After camber, I'll show a bit on the tendon losses. Go to result tables, tendon and tendon loss. Okay, so again the loss for different tendons could be checked from here for different construction stages. We can select the tendon we want from here, set at T10L and apply. So the stress after immediate loss. So in this case, since it's post tension, the immediate loss is friction and slip loss. So after the immediate loss, this is the stress. The loss due to elastic deformation is shown. The ratio in loss is shown. The loss due to creep and shrinkage, as well as the relaxation loss. Okay, so this is stress. Similarly, you can check the forces. I'll change this unit to kilonewton. So this was the force initially, and from that this is subtracted. At the final stage, so you can check the loss at the final stage. Okay, So force after loss, all losses, and force after immediate loss. So this gives you how much loss in the tendon force occurs. So 77% of the force after immediate loss, that is the force that will be remaining in the tendon at the end of the 14th construction stage. Okay. Similarly, you can view table for other variables. Say in tendon, I want to check the elongation. So you can check what is the elongation for the which tendon in which construction stage, how much mm it's elongating, what is the elongation in the element, and what is the final elongation value for the tendon at that stage. Also, you can check the stress limits in tendons. There are lots of tendons in this particular model, so the loading of this table will take time. In all, there are 72 tendons. Okay, so we'll check for a couple of tendons, say 1 to 5, and okay. Okay, so it asks us what the limit we want to set. So 0.7 of the ultimate say we are setting and say okay. Okay, so these are the values. I'll change the unit to Newton per mm square. So tendon stress allowable near anchorage is about 1100 Newton per mm. Acting near the anchorage is 1100 Newton per mm square, while allowable at the anchorage is about 1300 Newton per mm square. Okay, so this is how it is. Say if that is the general reduction factor, say we want to change it to 0.5 and say okay. So whatever tendons are failing, they will appear in red color. So this way we can easily check for a large number of tendons if some tendon is failing in the criteria. Okay. Okay, so that's it for the tendon loss. Now to perform the PSC design, we have already given the factors, and for this particular model, the PSC design has already been performed. So to check the PSC design results, you have to come to PSC, and then over here the result tables is provided. From here you can check the result for the pre-stressing forces. Say check for flexural strength. Okay. So we have designed only two elements, right? 17 and 28. That's why the option shown over here is for just two elements, 17 and 28. If you want to perform more design or select some other elements, then that could be done, and only those elements would be shown here. So in general, though there are 55 elements in the deck, only result for two elements would be shown. Say in kilonewton meter. So these are the design forces that would be acting, and these are the design forces for which it is designed. So if you'll go to the check column, you'll see everything is okay. Similarly, you can check for shear and torsion. In this particular case, most of them are a bit over designed, have to be for a safer structure, but it can be further optimized if you need it to be optimized. The results could be checked at construction stages as well. So which construction stage is critical? For 17 element at I and in 14th stage maximum is occurring, and for the other cases it's happening in the 12th construction stage. So these are the stress that are acting at the particular locations, at the top, at the bottom, the top left, bottom left, top right, bottom right, and out of all these, this is the maximum value of stress that is acting at that section, while the allowable values based on the codal provisions are stated in this column. So if the stress value acting is more than the maximum allowable, then again that element or that particular row would be shown in red text, so we can easily see where the issue is. Okay. Similarly, we can check the stresses at the construction stage. Okay. And the Excel report with all these things could also be created. For that, we need to generate the Excel report. About that will take about 2 to 3 minutes. So that too had already been generated. Just show the final report that's generated. So this is the final report that is generated. It will show what reinforcement we are providing and what is necessary, as well as I said, what our results are seen over there. All of those are shown over here. So there is 0 positive because it's a support section. So over here, the negative bending moment acting is this much, and it can the section is designed for much more than that, so the section is shown as okay. Similarly, check is made for shear, and the depth required and everything, all the calculations are shown. This area of concrete, area of steel. Okay, so this is for section 17 at the I end. Similarly, the results are shown at J end for the 28th element, 28th element at J end, the bending resistance, shear resistance, torsional resistance, the principal stresses, and so on. So this report is the data is generated over here just for those two sections, as well as this tendon stress check and everything is provided, whether certain tendon is failing or not. Okay, so just for the two elements, this figure report is generated. So now you can judge, right, that if the number of elements selected for design are more than this, then it will take quite a large amount of time. Okay, so this is for PSC design. Now to make the dynamic report, now if we want to add certain image to the dynamic report, then we can do that. So we'll go to results and check the mode shape, since we have done the eigenvalue analysis. So we are going to vibration mode shape. So we want to see the 8th mode of vibration. Okay, and say apply. So this is the 8th mode shape. Similarly, you can view multiple modes at a time. Say go to multi-mode, mode 1 to mode 4, and say OK. So basically in this case, 4 windows are created with the 4 mode shapes. As you can see, this is how the structure would be behaving for different mode shapes. If you want to check the modal mass participation, then you just click on these 3 dots. You select the modes. Okay, so here you can see in this how much mass participation is happening, right? Say here it's 78%, 78. So basically it should be more than 90. So more modes would be necessary here. Let us add the 5th mode shape. Or let us see some other mode with a different shape. Okay. So let us add the 12th mode shape figure to the dynamic report. So to do that, just right click, go to dynamic report image and say 12th mode and OK. So this image has been added for the dynamic report generation. Yeah, now let us check the deformed shape. Since we have performed the settlement analysis, just come to simple view again, view as before, and we go to deformation, deformed shape for the settlement case. So we'll be selecting minimum Z and okay. So here now we can see that the three supports that we had selected, for them 10 mm settlement is happening, while the one that was not selected, for that no settlement is happening. For that, when you are selecting certain set of supports for settlement, you need to assign that for that load case for a boundary change, because if you are not doing that, this settlement is applied for all the load cases. So what I mean is, you have to go to analysis, boundary change assignment. Within this support, this settlement group is created, right, to which all the peer bottom nodes are added. And then that it is once created, we have to assign that to the settlement analysis part. Okay, unchanged means it's simple. Just for the settlement analysis, that 10 mm settlement for the supports would be considered. So we say as settlement and we say OK. Okay, and if this is not done, then even for say the self-weight load case, the bending moment would be considered showing the 10 mm settlement. Now that won't be right, because what we do is we add the moments. We use the principle of superposition. So self-weight moment would be acting as it is. Besides that, if there is a 10 mm settlement, then what happens? So to check that, what we have to do is we have to create a load combination with self-weight and 10 mm settlement. So that would be giving us the resultant moments. So to check the bending moment or the reaction or the behavior of the structure just due to settlement, we have to check we have to assign the settlement load group to the boundary change assignment. Okay. Say we want to check the bending moment due to that. Sorry, beam diagrams. So this is the bending behavior due to that particular settlement. Okay. Now for the response spectrum, say RS in X. Okay. Similarly, we can check the deformations as well as the stresses due to that. And say we are adding the deformation due to the settlement minimum case. Say we want to add this figure to the dynamic report. Okay, so we have added certain data for the dynamic report. So to generate the dynamic report, in the tree menu we go to the report, and in the tools go to dynamic report generator. We create a new document. Okay, and over here let us say I'll be adding the response spectrum function chart. So okay, so this was the chart that was created right? Yeah, to add charts to the chart group in the report table, you need to go to works where that chart was created. So in this case, it's in response spectrum. So response spectrum function, and just double click on it. Okay, and you need to click this button. Okay, this adds the chart to the dynamic report. So this was done. That's why this was available over there. Okay. Similarly, we have created images for the mode shape. Okay. So say 12th mode. We just drag and drop the image. So the mode shape is added. Besides that, if you want to graphically view the tendon loss, then you can go to results, and there is this tendon loss graph option. Go to tendon loss graph. Say we are selecting the last tendon. Now this tendon is activated in the 10th stage. So say we are selecting 10th stage. So this is the force in the tendon at the beginning. And you can see as I am changing the stage, the force is decreasing. So this is the final loss at the 14th stage, that is after 40,000 days or so. This is the force that would be remaining in the tendon at that time. You can see there is some jump over here. This is the location of the peer table. Okay. Even tendon loss graphs could be added to the dynamic report. You just need to click over here. Okay. So graph for tendon loss was already added. So we go to the report. We say tendon loss for TP2 10 on the right end. And we add it. Okay, so the tendon loss chart is added. Besides that, if you want to add any table, say for any section summary, so we have used the internal diaphragm. So we just drag and drop internal diaphragm over here, and the table for with all the properties for internal diaphragm and the image would be added. Similarly, it could be done for reinforcement. So these are the things which at the end need to be submitted to the client. So it could be easily done over here. Not only that, say if there is any change in model, so you do that. And once again, when you perform the analysis, it's not like you'll have to generate the entire report again. Since the report is already linked to the model, what you have to do is you just have to go to tools and dynamic report auto regeneration. So once you click on this box will pop up. So you have to select the figures or the tables or the charts that you want to update and regenerate. So the report would automatically be regenerated. You don't need to do anything else again, and the copy just to be printed is ready. So this is about the dynamic report generation feature. Okay. Now, okay, so this is it for the session today, but I'll be taking the question and answers now. So if anyone has any questions, please type them now.